Okay, that gave me the usual recording in progress notification. Hopefully everyone else as well. So we're going to start with a few very brief announcements here. And just make sure I can pull up my screen sharing for that. Okay, are folks seeing the screen sharing here? Great, thank you. So yeah, since we're about 1 minute in already, I think we can probably start with the announcements at this point. So yes, I believe I just turned on recording and that all seems to have gone well. Today is a Rubin Science Assembly, October 31st, 2024. This is a tutorial type of science assembly. So we're going to run through a specific data preview 0.2, DP 0.2 tutorial here. And today's topic is a command line tutorial called the Rubin/LSST data butler from the command line. So this is intended to be an intermediate level data preview 0.2 tutorial in the command line category rather than notebook category. And I just wanted to mention that the Butler, it offers extensive functionality and documentation, and this is meant to be sort of like an intermediate version of demonstrating some command line invocations. So there's a lot more in terms of different functionality and more advanced functionality that one could imagine doing beyond what we're going to show today. Hopefully the slide advanced. So here is the agenda for today. We're starting with the announcements here for the first 5 or so minutes. And then for the bulk of the time, say until the last 10 minutes, time permitting, will be a run through of this command line tutorial 02 from data preview 0.2. And then at the end, time permitting, we'll hopefully have a little bit of open time for discussion and questions from the community. So there are definitely some news items happening, some announcements to make here. Some are in terms of Rubin Science Platform and Data Preview 0. So RSP, the Rubin Science Platform, has had its recommended image, which is another term for the LSST Science Pipelines version, updated to be weekly 2024_37 as of a month and a half or so ago, mid-September. Data Preview 0.2 Tutorial Notebook 04B, which is about the Butler, and specifically some intermediate queries there, was updated to work with a new Butler query system, which has been announced in a forum post from a month or so ago, which is an important forum post from LSST Data Management about updates to the Butler interface. And similarly, we endeavored to update the tutorial we're talking about today, tutorial 02, this week's topic, to reflect that same data management update to the Butler interfaces. We're in a phase now of the overall Rubin Observatory project where there are exciting news items coming out seemingly quite frequently. And so one example just from the past week was this publicly available Rubin Observatory news item entitled NSF DOE Rubin Observatory Test Camera Sees the Sky. So that's obviously a big milestone and exciting, and I would encourage you to check out that link and the article there for more detail from the project. There's also been some activity in the area of LSST survey strategies. So the Survey Cadence Optimization Committee, SCOC, released its phase 3 recommendations within the past month or so. There's a Project Science Tech Note on this topic, and there was also a community forum topic posted linked there, which is from right about a month ago. As per usual, we always try to mention and highlight the role and the availability of the Users Committee at the beginning of each science assembly. So the Rubin Users Committee is charged with soliciting feedback from the community about the Rubin data products and science platform and recommending improvements in their twice-yearly reports to the Rubin Operations Director. So you can find out more in detail about the Users Committee. You can check out their website, see the charge, more about the meetings, and also at the bottom here we have a list of the current composition of the Users Committee in terms of members. So with that, I believe that's the end of the announcement slides. So then I'll transition now into presentation of the actual tutorial at hand this week, which is, again, a command line tutorial about the Butler. So let's close this out for now. And let's go to this tutorial. Maybe someone could put a link to this in the chat if possible, because it's just a URL here. Note that because it's a command line tutorial, it's not like a notebook that you open in the RSP. It's actually a part of the Data Preview 0.2 website that just has a specific URL.
It's in there now. I put it in chat.
Okay, great. Thanks. I'm glad folks are ahead of me already. Thank you. Yeah, so this can also be navigated to from the dp0-2.lsst.io homepage by going to tutorials and then command line tutorials and then command line tutorial 02. So right off the bat, this is in the notebook aspect, and we'll show how to get there, but it's actually in the terminal command line. So, just to be clear and avoid confusion, the terminal command line is actually part of the notebook aspect. It's not a separate notebook aspect itself. It's not a separate terminal aspect itself. This LSSD pipelines version should be updated to 2024-37. That's my fault. My apologies for that. I'll work on that later. This can be run with a small container. So if you're logging in freshly to the LSST, to data.lsst.cloud, which is the Rubin Science platform, you could use a small container or a larger container, and it would be fine. So we'll get to accessing the terminal and setting up later. But I just wanted to give a brief overview of what this tutorial is about. So this tutorial is intended to introduce some of the command line functionality for what's called the Rubin LSST data butler, which is also sometimes referred to as the LSST Science Pipelines middleware. The idea being that the butler abstracts away any need for end users to know things like specific file formats or specific file locations or specific file names. And so all you should need to do is really just understand how to identify a specific data set of interest, for example, based on a sky location or a band, and then you ask the butler to retrieve that data, and it transparently grabs you that data or gives you a list of what data is available without you needing to do anything like ls in Linux terminal or find in a Linux terminal. So that's basically the idea. There's very extensive Butler documentation, which is linked here at the bottom of this first paragraph, which I would encourage you to check out. There's also two very specific areas of the Butler documentation that are especially useful in the context of getting started with Butler command line queries, and also just overall giving the context for what commands are shown in this tutorial. And those are specifically the querying data sets, which gives a lot of examples of how you do things like specify time intervals, for example, or specify ranges, for example, of detector labels. So I would encourage checking this out. This is one of the sort of early things one would need to check out to go further beyond this tutorial or further understand what's in this tutorial. And then there's also an important concept, which we'll get to later, of dimensions within the Butler, which is kind of this idea of parameters of how you would specify a specific data set that you're looking for within the broader Data Preview 0.2 repository. And both of these are linked from the starting location of the Butler overall documentation homepage within the LSST Science Pipelines documentation website, pipelines.lsst.io. So all of these are linked from within the tutorial that we're going through today, but I just want to make sure I highlight that right away, as it may make things go smoother to sort of just run through linearly the rest of the tutorial. So before getting started, the other thing I'll say is that this tutorial is demonstrating Butler in the context of a specific data set, which is the Data Preview 0.2 data set on the Rubin Science platform, and Data Preview 0.2 is simulated data that comes from the LSST science collaboration called the Dark Energy Science Collaboration. And so here near the start of this tutorial, there's links to more documentation specifically about the Data Challenge 2 DC2 simulated data set that Butler will be interacting with as we demonstrate the Butler's command line functionality today. Okay, so naturally getting started with the actual tutorial itself, the first step is to actually get to the terminal. So the first thing one does would be to go to data.lsst.cloud and then go to the notebook section. Again, the terminal is actually a subcomponent within the notebook section. So don't be confused about that. I'm already logged in, so we can't demonstrate exactly everything that you might see if you're not logged in currently, but one would click on notebooks. And if you aren't logged in, then it would require you to choose an authentication method to let you in. And then you'd also need to choose at this point a container size that would allow you to run the tutorial. In this case, a small container size would be just fine. And so that's what I have currently in this logged in version that I'm already in. You can see that towards the bottom of my screen here. It's a small 1 CPU, 4 gigabytes of RAM. And note that I have the latest recommended version of the LSSD science pipelines here, weekly 2024-37. So once you've authenticated and chosen your container size, then you would arrive at a screen like this. And so some of the first steps in this tutorial are to make sure that we get to the terminal. So the terminal is listed within the options available in this launcher window. It's actually under other, and it has this kind of dollar sign right here, if you can see it on the black background. So you click on that. And now we're in the terminal component of the notebook aspect of the Rubin Science platform. So let's go back to our instructions here. So we just logged into the RSP notebook aspect and we just started a Jupyter Lab terminal window by selecting the launcher by selecting it within other, sorry. And so now we're going to start actually issuing commands at the terminal, which is going to be what we do for most of the rest of this tutorial. So the first command is that we need to actually set up the LSST science pipeline software, make sure that's available within our environment. So the first command we do, which is also, as you might notice, told about in this help text you find here, is set up LSST distrib, which basically just brings the LSST science pipelines, including the Butler, into your environment here. So hopefully folks can all run that successfully. It shouldn't take long to run. This next command is in a sense somewhat optional because there's some nice functionality now in the bottom panel of the Rubin Science Platform window where you can actually just see visually by eye. It's always telling you that you have weekly 2024-37 is your version of the science pipelines. You can see down there on the bottom bar. Nevertheless, there's a command that if one is using a more strictly command line environment, you might be curious to run just to double check that you've got the correct version of the LSSD science pipelines, and that comes from this EUPS package management system, and it basically just lists what version of the LSSD science pipelines you have. So we can check here and run that second command, and it says, indeed, we have weekly 2024-37 in our environment now, which is great and matches what we see along the bottom bar in the Rubin Science platform. So yeah, naturally, I think the first command one would want to do when you are thinking about starting to run some Butler command line invocations would be to look at the documentation, look at the help, and Butler does provide very extensive and thorough documentation of its capabilities. So the way one does this in terms of a specific command is simply Butler, all lowercase, space, -- help, and we'll run that now. And you'll see basically that there's quite a lot of different functionality here that's provided. And so we're definitely not going to be able to cover all of this in this tutorial or in this session. But what immediately you can see is that there's a variety of different commands, and the ones we'll focus on later in this session are things like query data IDs, query dimension records. But there's much more beyond that if you would like to explore the help on your own more thoroughly. One thing that I would note is that, if you're thinking about this kind of behind the scenes, right, we just issued a command that starts with Butler. So that kind of implies that Butler is some sort of, you can think of it as executable available within your environment once you've brought in the overall LSSD science pipelines environment on the RSP. And so indeed, you can sort of, look at that in more detail if you so choose by doing which Butler, which is a Unix command, which basically tells you what an executable is based on its name. It gives you the full path to it. So the full path to Butler here is not important other than to show that indeed Butler is some executable that's living in your LSSD science pipelines installation on the RSP. And so you'll be able to invoke it because it's effectively in your path within this terminal environment. Okay, so that's kind of like the preliminary getting set up, running a very first Butler command. Now let's get into what I think would probably be of more interest scientifically, which is trying to identify specific data sets within a specific repository of data that you're interested in. So typically you'll identify a specific Rubin LSSD data set using 3 pieces of information. These are called the data set type, the data ID, and the collection. So you can think of the data set type as kind of like the kind of data you wish to identify, like a single band co-added image, or a calibrated visit image, or a co-add level source catalog. So those are different categories, different types of data sets that you might have within a data release, say. And then the data ID is a concept that has been covered in several of our tutorial notebooks within Data Preview 02. So for instance, there's a tutorial notebook about detecting and measuring sources in a custom COAD image. And there we use a data ID to specify a particular, what we call deep COAD image that we want to analyze and run source detection on. So there, the way that you fully and uniquely identify the custom COAD image that you're looking for is based on its tracked, patch, and band. So the tracked and patch both together specify the specific sky location, and the band specifies the LSSD filter. The collection then is the last piece here, and that's a string that specifies a particular set of persisted data for Butler to examine. And so the concept of collection is valuable because it allows for tailoring queries to work with either, say, the default Rubin provided DP0.2 datasets, or also, say, custom user created collections, or both. So you kind of need to specify a collection within the broader repository. And so, yeah, zooming out one level, collections exist within Butler repositories or repos, which a repo you can kind of think as the overall compilation of data that's managed within this Butler LSSD pipelines framework. And so on RSP, the standard Data Preview 0.2 repo of Rubin provided content is called DP 0.2, DP lowercase. And so therefore you'll see in many of the commands that follow, DP 0.2, which specifies the repo, is one of the key command line arguments that we're going to have specified as we run commands. So the first thing to do when we're starting out, getting a feel for exploring the DP 0.2 data set from the command line with Butler, is going to be to ask ourselves, well, what types of data sets are even available in this Butler repository? So as we saw from the Butler help command above, query dataset types is one of many possible command line invocations you can do with Butler on the RSP from the command line. And so let's just start out by doing sort of the simplest version of Butler query dataset types, where all we specify is the repository DP02, as I mentioned previously. So let's copy this from here directly into our command line environment where we've set up the LSSD pipelines. And you'll see there's quite a long list here. Even I was a bit surprised to see how many different dataset types there were, because the way that this has been set up is that, you know, different teams or different users have been able in the past to create their own collections, to do their own analysis that actually writes data into this Butler repository. And so there's, you know, presumably many different types of data that folks have added here or included here, which aren't strictly necessary to understanding at a high level the Data Preview 0.2 contents. But nevertheless, there should be some things that we recognize relatively well, for example, from the tutorial notebooks that exist for Data Preview 0.2. For example, you may recognize in that list deep coad, which are the deep coadded images, and deep coad underscore object, which are the object tables extracted from the deep coads, raw, which is kind of like the lowest level unprocessed data, calyx, which is like the processed visit data, bias, which is a type of calibration data that one would use to reduce the data from raw to calibrated, source, which is the source tables, and so forth. And again, one interesting thing you can do here, if you want more information, is that you can do Butler query dataset types minus help to get help specific to this query dataset types invocation pattern of the Butler command line tool. And so that will show you arguments specific to this particular command within the broader Butler framework. Okay, so that's a very first example of query dataset types, and that will help us to understand what we might ask for with future Butler commands, now that we know some examples of the names of these dataset types that we could go looking for within the DP02 repo. The next thing that I wanted to illustrate, because it is one of the first most useful types of Butler command line invocations you might want to use to explore a repository, is called Butler query-dimension-records. And the idea here is to get a sense of what are the unique possible values along the different dimensions that specify specific data sets. So I linked and I showed earlier this very helpful LSST pipelines documentation, specifically more about the concept of dimension. I don't want to belabor it here too much, but they're summarized as astronomical concepts that are used to label and organize data sets. Examples of dimensions include instruments, detectors, visits, and tracks. So you can kind of think of a dimension as any type of parameter you might use to help fully specify a data set of interest. And then so where Butler query dimension records, the specific command comes in, is that it can give you lists of the unique values that dimensions can take within your repository. And so we'll see some examples of that going forward. The first one I thought would be interesting to look at would be to query what the values along the band dimension are, where band is another word for the filter, or what filters are available within the full data preview 0.2 repository. So let's go ahead and try that. If we look back at the help, we can see that the first argument to, well, we can look at the help now. So let's look at the query dimension records help. The first argument is the repository. As I mentioned, that's the string dp02. And then the next parameter that one specifies is the dimension along which you're interested in. And so here, that's why our command looks like Butler query dimensions, dp02, the repo, and band being the name of the dimension that corresponds to what you might otherwise call the filter. So let's try running this and see what we get back. So here's the list of the different filters that are available within dp02, the full repo. To me, I was actually a little bit surprised to see how long this list was. There's more than just U, G, R, I, Z, and Y, right? There's actually some other stuff. I would say that, for the purpose of end user interactions with the data set, let's not worry about what these other things are. They're really from early engineering tests, basically. But nevertheless, it's interesting to see that we can reveal a full list of filters that are in the dp02 repo, and they do indeed include the ones you would expect to see, U, G, R, I, Z, Y, within the data preview 0.2 repository on the Rubin Science platform. So that's kind of like a first example of using query dimension records to see along a specific dimension, what are the possible values that you can have within this repository. Okay, so now let's continue on this path of looking at the single dimensions and what values they can take for relevant parameters for trying to identify data within with the Butler within this dp02 repo. So yeah, for several commands later in this tutorial, what we want to do is we want to restrict to images within the images or data within the dp02 repo that comes from what's called the ImSim image simulation tool. And so actually the data preview 0.2 repo contains data from both the ImSim tool and a lower level tool called PhoSim, which is the photon simulator, which we don't want to focus on here as end users. But nevertheless, it's an interesting illustration of how one restricts to the data that one wants by using Butler command line functionalities. So let's again do a very similar command to what we just run before. But instead of specifying band for the dimension, let's specify instrument for the dimension. And so we should get a list of the unique instruments that are in this Butler repository. And indeed, you can see that there's LSTC Cam ImSim. So that's the one we want. That's like the high level image simulation instrument. And then you'll also notice that there's PhoSim, which is a lower level type of data product, which we don't want. So this has been a valuable query in that it shows us that there's multiple different instruments in the data set, which we'll need to take into account with future Butler commands later on in this tutorial, because we want to restrict to the high-level IMSIM products, not the lower-level FOSIM products. Okay, so let's continue down this path of looking at different dimensions and what values that dimension can take. So we're going to do a very similar command to the past couple that we've done, but now with detector, which detector is another word for CCD here. So let's look at what are the possible values of detector within the DP02 repo on the RSP. And you'll get a list of several hundred items here, which makes sense because of the number of CCDs that are on the LSSD focal plane. You will notice again this same situation where there's a mixture of FOSIM and IMSIM instrument detectors here. And so in the next couple of queries, we'll show how to make sure that we continue restricting to the IMSIM high-level image simulation products that we care about. Okay, so which brings us, the idea of restricting to a specific subset that we care about within the broader repository brings us to the point and the important point that these Butler command line invocations have a kind of SQL, ADQL-like query syntax where you can add a -- where clause to your command line invocation to restrict the data down to a specific subset of what you want. And so now that's what we're going to get into. And many of the later commands in the rest of this tutorial will also use the same -- where syntax to restrict to specific types of data or specific subsets of data. So the first example here is this command. So let's try to copy and paste this command where we have a where clause that says where instrument equals LSSD cam IMSIM. So that's restricting to the high level software simulation instrument. And then there's also, I put in an additional and clause here where I did a range of detector ID just to limit the output so that we don't get bogged down in too much output. So here is the full command. Let's take a look at this real quick. So again, we have Butler query dimension records as the start. The next parameter is DP02, which is the repository. Detector is the dimension that we're interested in querying. And then there's the - where clause, which is the new element we're introducing here. Note that where the argument to the where parameter is a string enclosed in double quotes. And then within that, you specify constraints in a way that's similar to, say, SQL or ADQL. And again, for full documentation on the syntax of how you make these constraints, I would point you back to the same querying data sets, very nice documentation page for the LSSD science pipelines, which we pointed to earlier. So let's try running this. And the important thing is that we want to see only detectors 6 through 8 if our query has been constructed correctly. And we want to only see detectors from the LSSD cam IMSIM software simulation instrument, not FOSIM. So let's see if we were able to achieve both of those. Okay, so indeed, it looks like this all worked, right? Because now we only see dimension results for LSD cam IMSIM, and we only see detectors with ID labeled as 6 to 8. You'll also see that there's some other columns here, which you can kind of think is like the metadata associated with that dimension. So, each detector, in addition to having a detector ID, that's like a number, it also has these other parameters like its full name, it's wrapped. If you recall, the LSSD focal plane has lots and lots of CCDs, right? So its CCDs are broken out into groups of 3 by 3, which are called rafts. So the dimension here is really the detector, the CCD, but nevertheless, you're also being shown various metadata that helps to fully define each possible value that could be achieved in this dimension of detector. Okay, so let's try to go one step further now with the idea of being specific about what we want by using this where command line argument. And so one natural thing that one might want to do in this regard is not just restrict by the detector name, say, or detector number, but plausibly you could imagine for some science case that you would want to restrict to a specific area on the sky, so do a spatial restriction. And that's what this next command line invocation shows an example of. So let's start by copying this over into the command line environment on RSP. And then we'll take a look at, maybe I can zoom in. Well, if I zoom in, then the command will take multiple lines. So we can, I'm not sure if we want to do that. But we again start off with the first two arguments being the repo. Note now that the second argument, which is the dimension, is actually the exposure. So we're going to be looking at the possible values that an exposure could take on, subject again to the where clause, where the instrument is IMSIM, the high-level image simulator. But then note that now there's a couple more and clauses here, which specify the RA. So we're going to look at a narrow slice of RA as just an example here. So let's do this, and you'll see the output. Again, you find basically a list of exposures and also their metadata associated with them. And so one thing you notice in the metadata is that the RA index of the exposures is actually given by a parameter called tracking RA and tracking dec, and that's why we have tracking RA and tracking dec in the exposure rather than just .RA or .dec, is because actually these parameters within the dimension record are referred to as tracking RA and tracking dec, so we need to use that correct syntax to refer to the coordinates here. And so what you see is that I believe we have 9 total results here in this very narrow range of right ascension. If you were to try this query without the spatial constraint, without restricting to a narrow stripe in RA, you would just get many, many more results. And actually, one aspect of the recent updates to Butler, which was pointed to in that forum post from last month, is that if you were to take out these RA requirements here, you would run up against the default limit of 20,000 results that you would get from a Butler query. We'll talk a little bit later about how to change the limit to be smaller or larger than that. But this is kind of an example, a more science-like example of restricting to a specific spatial region using this Butler query dimension records command line tool. Okay, so I think I explained all the parameters already. So let's also try now, when you think about science cases you might want to do, especially with LSST, there's spatial queries, but also LSST will have an extremely strong time domain component, right? And so one thing you might naturally want to do is, say, try to find the list of exposures within a specific time interval. So let's do that. That's the next command. Excuse me. So let's copy and paste this next command into the RSP terminal and then have a look at it in detail. I'm sorry, I didn't want to. So let me also just hit enter on it as well. Shouldn't take long. So again, we're running Butler query. Okay, so yeah, let's back up a step because this is the first time we're, it looks like the first time we're doing query data IDs. So query data IDs is another version of another command line invocation one can do with the Butler. So let's just quickly look at the help for that before we do a specific command. So this is another way of querying the data in a repo. Now, Butler query dimensions, that's about looking sort of along a single dimension, right? But query data IDs is kind of like more inherently multidimensional because a data ID usually takes more than one piece of information to specify the data set, right? So, an example of a data ID that we saw earlier was track, patch, and band. So query data IDs is, in some ways, you can think of it as similar command to what we were looking at of query dimension records, but in this case, we're querying data IDs, which is identifiers of specific data sets rather than values along a single dimension. And so again, you have the repo is the first parameter here. So we're going to keep using DP02 for that because that's the main repo on RSP. And then you can also specify specific dimensions that you want to look along as well. So you could get all the dimensions or you could specify specific dimensions. So I believe this command that we're going to look at here as a first example does specify a specific dimension that we want to look at. So now we're using Butler query data IDs with the DP0.2 DP02 repo and along specifically the exposure dimension. And we're going to do a where clause that intentionally brings in an example of a time interval constraint. So again, we start with the instrument equals LSSDKM IMSIM because we always want to do that now that we know that there's other software instrument in this that we want to exclude. And then here's the key syntax with the after the and clause about finding the relevant time interval. So there's exposure.timespan overlaps, and then you have this set of brackets that encloses two timestamps, and each timestamp is expressed with a T and then single quote enclosed date you can think of, basically. So again, this is another case where I would refer back to the documentation from the LSSD science pipelines, but this querying datasets page really has a great explanation of all the different specific syntax one uses to define like time intervals, timestamps, etc. So there's much more information there that we don't have time to go through all of it today. But let's try running this and see what we get. So you'll notice that this is a very narrow time span, right? It's like a couple minutes, basically, a couple minutes plus, which was the idea because there's a lot of exposures in the whole data preview 0 to repo. So we don't want to show them all here. But anyway, you can see that this time span syntax has indeed limited you to a very short time range. And you can also see that the exposure numbers are consecutive, right? Which kind of makes sense too, that you would have this very narrow couple minute time interval, and naturally the exposures end with 44, 45, 46, 47. So I think this is all hanging together well. So yeah, one thing you'll also notice here is that this command line example uses what's called the overlaps operator. You can see that we said exposure.timespan overlaps with this specific sort of tuple-like expression that we have that gives the beginning and end of the time interval of interest. So again, the overlaps operator is explained and discussed in more detail in the same querying datasets page within the LSSD pipelines documentation. Okay, so let's continue on down the path of further querying data ID values. We already did look at the Butler query data IDs help. So now let's look at the Butler. Let's look at some other ways of querying data IDs beyond just illustrating a time-constrained query. So here we have an example now where we're going to look for not exposures, but we're going to look for specific data sets that are available within DP02. And in this case, we're looking at a higher level product called Deep Coad. So Deep Coad is mentioned in many other Rubin science platform DP02 notebooks. Basically, a Deep Coad you can think of as like a deep sky image made by co-adding all of the good available LSSD data at a fixed sky location, as opposed to, say, a good seeing coad where you had made further cuts on making sure that you have images that are sharp, high angular resolution. So Deep Coad products are very useful, which is why I chose them for this, because you could imagine studying faint galaxies or distant stars in the Milky Way using these Deep Coads. So let's try an example now of query data IDs, but with Deep Coads rather than exposures. So let's copy the command and let's look at it for a second. So Butler query data IDs is the command we're going to use. DP02 is the overall Butler repository. Tracked is an optional argument, but it's the dimension we want to look on. So the question we want to answer here is what tracks are there among the data sets of type Deep Coad within the DP02 repo on RSP. Here we're explicitly specifying the collection. So the reason I'm doing this is because in the past, we didn't explicitly specify collection, and that was just essentially just saying, look at all the collections. Here, I figured we should look at the official collection for the DC2 DP0.2 outputs, which has this name 2.2i/run/dp0.2, which you may have seen in other tutorials before. And then there's the minus datasets argument, which says I want to know what the tracks are in the set of Deep Coads that are available within this repo. So let's just try running this, but you'll also notice there's no where clause here, right? So we should expect a relatively long set of outputs. Okay, and indeed we get a much longer set of outputs than we got for the previous commands, although it's still on the order of 100 to 200 total outputs. So here, what we have is the sky map listed and the tract. So the reason the sky map is listed is because you need to know the sky map in order to fully specify the tract. So you couldn't just say tract 2897 because that's actually not a full specification of a tract. You need to also specify the sky map. So that's why that's also listed here. And for the sort of official DP 0.2 data products, the sky map is always called DC2. Excuse me. So then let's take a look at these outputs in further detail. I'm guessing, that even I don't really recognize these tract names all that well. Just, these 4-digit codes, basically. But we can ask some sort of simple questions to try to understand whether or not this output makes sense, whether or not we've gotten the right list of tracks for data preview 0.2. So one way of doing that would be to look at how many results you got. So the next command line invocation is going to ask the question of how many tracks did we get within data preview 0.2, and does that make sense with what we know about data preview 0.2. So let me first copy this command in. So let's take a look at this. So we have exactly the same command up through the minus data sets argument, but then I've appended a few items here that come from the realm of what you can do at the command line more generally than just what's available from the Butler. So actually what we're doing here is we're recognizing the fact that this command up through the datasets argument is creating a bunch of output to the terminal, and we can treat that like any other output to the terminal. So we notice that in the above, right, every data entry in the output has DC2 in it in the printout. And so let's use the grep functionality to only restrict to those lines, only the actual outputs, not the header metadata, where the sort of header metadata, I mean, the column listing. So let's restrict to only the data lines, and then we can also pipe. So the vertical line is a pipe is referred to in Unix, and we can pipe that to the WC utility, which counts. So if we do this, what we're doing is counting how many outputs we got within this query. So the answer is that we got 157 tracks in our query within data preview 0.2. And if one looks at the DP 0.2 data set in various ways, whether it be through the portal or through the DP 0.2 data products definition document, you'll see that this is a match, which means that this is all kind of hanging together, that we get from our query where we're asking for what is the list of tracks represented within all of the deep quad data sets of data preview 0.2, we get the right number of tracks. So that's encouraging, and it's also a good example of how you can treat the Butler command line output just like you would any other command line output, and say redirect it somewhere else or pipe it somewhere else for further saving or analysis that you might want to do. So then the other thing that I think is a good sort of initial check to make sure that we're understanding all the outputs we're getting here, at least initially, is to zoom in one level lower instead of the tracks. With the tracks are the relatively large sky regions within an LSSD sky map. Let's look now at the patches and see if the number of patches makes sense with respect to the number of tracks that we just found. So let me start by just copying and pasting a variant of what we have here. So the Butler command we're going to use is almost identical to what we did before, the same. It goes up through this specifying the dataset type of deep coad. But then we want now the dimension to be patch. So we want specifically a list of patches represented within the deep coad datasets and their data IDs. So let's look at this. And as you might imagine, because there's many patches for each tract, because the patches are smaller in spatial size, we're going to get a longer list. So let's just first have a look by eye at this longer list. And indeed, you can see now that there is a much longer list of outputs I won't try to scroll all the way up because I think it's actually thousands of patches that make up DP02. And so the columns in this case that are being displayed are the sky map, the tracked, and then the patch. And again, the reason for that is because to fully specify the patch, you need those prior two columns that come to the left here. You couldn't just say patch 12. To fully specify the patch, you would also need to know what tract it's within and what sky map that tract is within. So now let's go back to the actual tutorial and paste in the full command that illustrates the counting of the patches within data preview 0.2 deep coad. So here again, I've just appended some of this Unix type of piping. So again, we use the grep to isolate to only the query results rather than trying to count as well the column headers. We don't want that. And then we also pipe to the WC Unix utility, which does the actual counting in the end after we've restricted to only the data rows. So the idea here is that we should see a number that we can explain based on how many patches we know are in each tract and how many tracks we found originally. So let's see what the number was. Should be, I believe, in the thousands here. So yeah, there's actually almost 7,700 patches that have deep coad data products within the full DP02 repository. And that number indeed makes sense because as we just saw, there's 157 tracks. And we know from the data preview 0.2 data products definition document that each tract is subdivided into 7x7 grid of smaller patches. And so there's 49 patches for each complete tract. And indeed, if you were to, do the multiplication of 157 tracks times 49 patches per tract, you would get exactly the same number, 7,693 patches in DP 0.2. So all of this hangs together and just goes to show you some examples of how you can explore the data from within the command line, specifically using Butler to try to make sense of all and explore everything that's in the repo. So I just wanted to end with a couple examples that illustrate relatively recently added functionality. This was, again, going back to the community forum post I linked to earlier in the announcements about recent updates to the Butler. So here we're going to show two specific new functionalities. One is limit, which may sound familiar from, say, SQL queries you may have done where you want to use limit to only show a certain number of results, and then order by, which is a way of sorting the outputs in a certain way that suits what you're trying to do. So let's first look at an example of using limits. We're going to go back to the same command that we just issued, but now add a limit argument. So let's take a look at this. This is exactly the same command that we just did, but we got rid of the sort of post-processing here from the Unix utilities. But what we added instead is a minus limit 4. So if you remember, without the minus limit 4, what we saw was that this query for the patch values within the deep coad data sets in DP02 is a very long list, thousands. So if you just wanted to get a flavor of what the output is without having thousands of lines printed to your screen, what you could do is append this minus limit space 4, which means only show me a set of 4 rows of the output rather than showing everything. So let's take a look at that. Shouldn't take too long to run. Mine's already finished. And indeed, what you can see is you now see nicely the headers here, which show you the column labels, sky map, tract, and patch, and only 4 data rows. So this could be useful if you're just trying to initially explore, what are the different possible patches in here and how are they defined, for example, with sky map and tract without having to see thousands of lines printed out to the command line. You could, of course, change this number, right? It could be 5, and then you would get 1 extra result as well. It's user configurable, which is what's nice about it. One thing I would note is that there's a default limit of 20,000 implicitly in your Butler queries. So that's something to, I guess, watch out for, is that if you suspect you're issuing a query that has a huge list of results, you may want to explicitly specify larger value of the limit so that you don't run up against the 20,000 limit. One nice thing though is that if you do run up against the 20,000 limit, Butler will print out a warning to the command line to sort of alert you that you're running up against a limit in your query size. Okay, so as a last example that I wanted to show, I think we're pretty well on time here, is that in addition to this new limit argument, you can also have this new order by argument. And so we'll show an example of that. Let me copy and paste this last command from the tutorial in. So here we go. So the thing to focus on here is that I've added the order by parameter here. As we saw earlier, one of the outputs that you get is this so-called full name of the detector. Yeah, here we go. You can see that we saw this earlier. Yeah, detectors have something called a full name, which is like a string that has this kind of structure to it. And so we can choose to sort by that. So that's what I'm doing here. I note also that I've included the limit parameter because I just want to show the column headers in a few examples, but we don't want to see every single detector necessarily. Okay, so indeed, we've sorted by full name here, right? Starts with R01-S00, next one is R01_S01. So these are useful new additions to the Butler interface that I thought were worth highlighting in light of the recent forum post from data management last month. And we're at 8 minutes until time, so I think we can leave it at that and have time for discussion. End early if people would rather end early, but yes, thank you for your attention on this I know this is a very highly technical topic that involves lines of code more than pretty pictures, so thank you for bearing with it.
Hey, thanks, Aaron. Hey, I have a question. Like when you showed the bands, there were a lot of things besides UGRIZY, and that's just engineering learning about how stuff works. And I know there are other files like that. Will DP1 have those cleared out?
That's a good question. Maybe a question more for Melissa than me. One thing I would say is that, Melissa, do you want to take that or you want me?
Yeah, I could say for DP1, the Butler will look much different. So it should be, yeah, you won't be able to see everybody's stuff. It should be read-only. Things are going to change about how when you want to do some reprocessing, it's going to be different. So expect things to be quite different in terms of, so Butler, like querying, searching for data, using butler.get to grab stuff, that kind of will all stay the same. So it's good to learn those kinds of things, but some stuff about how the data is set up is going to be different.
Thank you. Oh, Aaron, do you know on the time span, the overlaps command, is that inclusive between the boundaries? Does that include the beginning and the ending time?
That's a good question. I would suggest going back to the documentation to look at that. Conceivably we could try it ourselves, right? And see what, to me, it seems like a bit of a weird, it feels a little bit like a pathological edge case of like you specify a time interval that exactly matches the timestamp of an exposure, but we could try to look at it now and see. Okay, so I didn't specify the timestamp here. Maybe this will be hard to do in real time. One thing I would say is I would go again to this data set, to this querying data sets documentation and see if there's a specific statement, but you could also imagine concocting a query to test it out, right? And just see what happens. So that's what that would be my first two lines of thinking of what one would do here. Yeah, I'm a little bit hesitant to try to read the documentation. right now in real time. But
Yeah.
yeah.
On that topic, I was trying to go and figure out whether when you specify that like begin and end for your time span, whether it only returns exposures that took place entirely, like were contained by that, or if they either their start or their end overlapped with that. I couldn't find from the docs, so yeah, we might have to test a bit.
It seems like it might be more important with, overlap with other queries besides time. So I was just curious.
Yeah, so we saw one example with detector, right, where it was clearly inclusive. That where we did it was the one that had the syntax 6.8. Yeah, here we go. Right, so detector in 6.8, and that showed us 678. So that was clearly inclusive, but it's a little, yeah, the timestamp, it just feels like more of a contrived example to me to specify a timestamp that like perfectly lines up with the timestamp of an exposure. But I think one could concoct an example to test it out relatively easily if it's not already just set in the docs. Yeah, is that Tim that has a question?
Yeah, but can you please answer Jovan's question in the chat first, because I think it's more generally applicable.
Oh, sorry. I can't. I haven't been able to see the chat since I started sharing my screen. So, I guess let me stop sharing my screen so that I can find the chat. Does anybody know the timestamp of this?
9:55, I think it was last one.
Okay, sorry. Yeah, I started scrolling all the way up to find it. I had assumed it was from a long time ago. Yeah, that's a good question. I'm not sure. I'm not sure in generality what the answer there is. You may that's a pretty highly technical question. I think we could follow up on the forum or elsewhere about that. Does anybody else know whether doing limit something is only retrieving those rows or whether it's retrieving all the rows and then subselecting? I would kind of guess it does the latter, but I don't know the specific code here that exactly, like I couldn't point you to the line of code that says definitively what it's doing. That's a good question. I'll note this down and try to follow up after the fact because it's a good point. You'd certainly hope it goes faster. Yeah, Melissa, or sorry.
Yeah, it's a good question because like with ADQL, I think there is a difference whether you're doing top or limit. Where top, I think it does it all, then gives you the top, whereas limit, I think it stops once it gets to your limit. But I don't know for the Butler, so we might be able to provide better guidance. It's a good question.
Yeah, I would also say it might depend on whether you have like the order by in there, right? Because you can't, yeah, because if you're ordering by, then that kind of implies you were looking at everything to put them in order, which may have been the reason why this was slow or not faster than expected. Yeah, I mean it's a good point you're saying about how it seemingly took several seconds. A lot of that could be initial latency of just connecting to the database, right? Though, so it's hard to. I mean, that's why I'm hesitant to like do timing tests here and try to figure that out. I think the way to figure it out might be to specifically choose a case that would return a huge number of results, and then maybe that would at least try to limit the latency aspect here, muddling up the picture. But yeah, it's a good question. I think we'll follow up on that because I can see why, as it was said, that's a generally useful thing to know. Yeah, Tim, was there a?
Yeah, my question's even more nerdy. So the timestamps in Rubin are in TAI, International Atomic Time. I was wondering if the Butler is going to implement the conversions from UTC, which is probably what users are going to use, into TAI, or whether users are going to have to do that for themselves. I keep track of when leap seconds get inserted.
Yeah, there's some discussion of TA. If you go to this time literal section, yeah, I'm not sharing my screen anymore. My best advice would be to look at the specific time literal section of the querying data sets aspect here that we were looking at earlier of the documentation. But there is clearly some discussion of MJD, TAI, etc. And so I would look at that as a starting point. And then, if there's, I agree, this is really a tricky issue of handling all these conversions in detail at the leap seconds. So I think I would probably look to things like the data products definition document, which is a formal project document. And if it's not there or in this documentation, then try to ask on the forum is probably my advice. But I don't really want to try to read this in real time and then try to,
Yeah, I
this is a
wouldn't
very detailed
recommend the
thing.
details of timescales in real time, as it were. Yeah, thanks.
But there's clearly some support for, say, MJD. So it's not there's different time formats you can use. That much is clear. Yeah, I mean, it says by default the parser uses UTC being one option among several. So, but this is all very tricky stuff. I don't I don't want to try to make more comments on that in detail. Okay, well, we're 2 minutes over, so I guess we should probably stop. But thanks everyone for attending this very highly technical talk. I really appreciate it. Obviously, very great questions as well. So was it Bob that wanted to have a discussion, or was that already addressed in the chat? Again, I couldn't see the chat.
Well, let's see, Karen, it was really helpful. That
Okay.
was a great talk, Aaron. I got a lot out of that. I appreciate it.
Okay, yeah, thanks, Bob. Thanks everyone for attending, and check out the schedule for future events.
Nice, thank you.